Explainer. Today we're tracking one of the most fascinating protagonists in the entire universe, a single ray of light. Let's just dive right in, shall we? Our story today explores exactly what happens when this intrepid little light ray goes on a journey and hits a boundary. I mean, does it bounce right off, or does it bend its way on through? As you'll see, we're going to decode the absolutely beautiful, predictable rules that govern exactly how light behaves.
So here's our quick roadmap for today. We've got 1. The laws of reflection, 2. Forming images with mirrors, 3. Mirror math and conventions, 4. Refraction and bending light, 5. Forming images with lenses, and finally 6. Lens math and power. Let's get to it.
Starting us off with Section 1, the laws of reflection.
Okay, it all starts with a super foundational definition. Reflection of light is simply the bouncing back of light when it hits a polished surface, like a mirror. Think of it like throwing a tennis ball against a smooth brick wall. It doesn't go through, it rebounds, right? But with light, this rebound isn't just some random ricochet. No way. It follows strict, unyielding laws.
And you can see that exact predictability right here. Notice how our incoming light, which we call the incident ray, hits the mirror. Now see that dotted line standing straight up? That's our normal. The very first rule of reflection is right there in the math. Angle I, the angle of incidence, perfectly equals angle R, the angle of reflection. Plus, the incident ray, the reflected ray, and that normal line, they all exist perfectly flat in the exact same plane. It's just pure visual symmetry in action.
Moving on to Section 2, forming images with mirrors.
Now, what happens if our polished surface isn't flat? Well, we can actually curve our mirror in two distinct ways. Take a look at the left side. We have a concave mirror. Notice how the reflecting surface literally caves inward? This specific shape forces light rays to gather or converge together. But on the right, we've got a convex mirror, where the reflecting surface bulges outward, spreading or diverging those light rays apart. So two totally opposite shapes giving us two totally opposite results for our traveling light ray.
And here's how we make sense of all that bouncing light. The step-by-step methodology brilliantly simplifies the chaos. To figure out exactly where an image will form in these curved mirrors, you don't have to track millions of rays. Actually, you only need to track 2, because where 2 rays intersect, boom, your image is formed. The rules are basically a cheat sheet. First, if a ray comes in parallel, it bounces right through the focus. Second, if it goes through the center of curvature, it just bounces straight back along its own path. And third, if it hits dead center at the pole, it reflects perfectly symmetrically.
When you apply those cheat sheet rules to different object distances, you get this really wonderful summary table. But I want to highlight one specific amazing pattern here regarding convex mirrors. Look closely at that data. Convex mirrors are incredibly consistent. No matter where you place an object in front of a convex mirror, it safely produces a virtual, erect, and diminished, meaning smaller, image every single time. That's exactly why we use them for rear-view mirrors in cars, right? They always give you a nice, wide, upright field of view.
All right, Section 3, mirror math and conventions.
Now, I know math can sometimes be daunting, but don't let these equations intimidate you. It is all anchored in physical reality using a really simple Cartesian grid, literally the exact same kind you've drawn 100 times in math class. The pole of the mirror is the origin, right at 0. Everything to the left, which is the space in front of the mirror where the light comes from, is negative on the x-axis. Everything to the right, behind the mirror, is positive. Same goes for height. Above the principal axis is positive, below is negative. Pretty simple, right?
So the really crucial point here is how this grid powers our formulas. The mirror formula is 1 over f equals 1 over v plus 1 over u. Here, f is focal length, v is image distance, and u is object distance. And then we have magnification. M equals negative v over u. Because of that sign convention we just talked about, this magnification number literally tells us the nature of the image. If m is negative, your image is real and upside down. If m is positive, your image is virtual and standing upright. The math just does the talking for us.
Let's pivot to Section 4, refraction and bending light.
So, this brings us to the ultimate question for the second half of our journey. We know how light bounces off a mirror, sure, but what happens when it passes straight through a surface into a totally new medium? Say our light ray protagonist hits a pool of water or a thick block of glass. It doesn't just stop, it pushes right through. But it doesn't survive the crossing unchanged. And that brings us directly to the concept of refraction.
Simply put, refraction is the bending of light when it travels from one medium to another. But why does it bend? Well, it's actually because light travels at different speeds in different materials. The rule for this bending is beautifully simple.
If light goes from a rarer medium, like air, into a denser medium, like glass, it slows down and bends toward the normal line. But if it escapes from that denser glass back out into the rarer air, it speeds up and bends away from the normal. Basically, the speed dictates the steering.
Let's actually see this in action. I want to walk you through this brilliant setup of a rectangular glass slab. Watch how the light ray enters from the air, hits the glass, and bends toward the normal. Then it travels down, hits the bottom boundary, exits back into the air, and bends away from the normal. But here is the absolute most fascinating detail. Because the medium on the outside, the air, is exactly the same on both sides, that final emergent ray exits perfectly parallel to the original incident ray. It just gets, well, shifted over a little bit.
Which perfectly sets up Section 5, forming images with lenses.
Scientists harness this exact bending property using lenses. Let's compare their physical shapes visually. On the left, we've got a convex lens, which is thick in the middle. That specific shape forces light rays to converge to a single point. Now on the right, a concave lens is thin in the middle, forcing light rays to diverge or spread out. Notice how the lens that's thick in the middle gathers the light, while the one that's thin in the middle scatters it. It's a great physical anchor to remember how they work.
Now, earlier I promised you that this journey is completely predictable. Take a look at this summary table for convex lenses. Does it kind of look familiar? It absolutely should. The rules and outcomes for a convex lens act as a clever, cognitive load-reducing remix of the concave mirror rules we learned in Act 1. It turns out, nature really loves a pattern. By mastering one, you've secretly already mastered the other.
Almost at the finish line. Section 6, lens math and power.
And just like the image rules, the math is a remix too. Notice this critical, easy-to-miss difference. For mirrors, the formula is 1 over f equals 1 over v plus 1 over u. But for lenses, we just flip one sign. It becomes 1 over f equals 1 over v minus 1 over u. Honestly, that single minus sign is literally all that separates bouncing light math from bending light math.
And when we're dealing with lenses, we also talk about their power. The power of a lens is simply its ability to converge or diverge rays of light. We calculate it as the reciprocal of its focal length, so power equals 1 over f. But listen closely, here is the critical trap to avoid. For the power to be calculated correctly in units called diopters, that focal length absolutely must be measured in meters, not centimeters. Always convert to meters first.
Okay, before we wrap up, let's highlight a really surprising edge case. We said refraction is bending, right? But what if the light ray hits the new medium perfectly straight on, right down that normal line? Well, in this case, the angle of incidence is exactly 0 degrees. And because of that, there is absolutely no bending. The ray passes straight through to the other side, completely undeviated. Kind of a cool exception to the rule.
So we followed our light ray from bouncing perfectly off flat planes to gathering in curved bowls to bending its way through solid glass. By understanding the laws of reflection and refraction, we unlock some truly incredible potential. So I want to leave you with this final provocative thought. If you now know exactly how lenses bend light and mirrors bounce it, how might you stack them together to peer into the microscopic world of a single cell, or to look deep across the infinite expanse of the universe? The principles you've learned in this explainer today are the exact same ones powering every microscope and telescope in existence. Thank you so much for joining me on this illuminating journey, and keep exploring.